Hi, welcome back to Math310, Ordinary Differential Equations. This is lecture section 5.4 on Euler equations and regular singular points. So we're going to take a look at an important differential equation today, the Euler equation, and we're going to see how to solve that. And we're going to see actually remarkably that many second order differential equations can be basically look like the Euler equation near their singular points. So that's the sort of overarching motivation for taking a very careful look at the Euler equation. So first of all, let us understand what is a singular point. If we have a second order homogeneous differential equation like we have here, and we identify the coefficients on the y double prime, y prime, and y, and those are functions of x. So they're not constant coefficients, but they're also but this is also still linear, okay, because those things are all just functions of x. So that second order differential equation has a singular point at x naught if p of x naught is 0, provided that x minus x naught is not a common factor of p of x, q of x, and r of x. So that means basically you can't divide it out. Let us just look at some examples. I think this will become really clear. Let us also just recall in the last lecture we talked about series solutions near ordinary points. So just to remind ourselves, non-singular points are called ordinary points. Okay, let's get some examples of some differential equations and identify the singular points. Let's get an example here. So here's a differential equation: 1 minus x squared y double prime minus 2x y prime plus y equals 0. Okay, it's linear, it's homogeneous, it's non-constant coefficient. What are the singular points? The singular points are when this leading function here is 0. So the singular points are at x equals plus or minus 1, because that means 1 minus x squared will be 0. Okay, next example. Here's another equation: x minus 1, 2x minus 1, y double prime, plus 2x y prime, minus 2y equals 0. Okay, we take a look. Where is this thing equal to 0? And that is going to be singular points. That will be, let's see, x equals 1. That's when this first factor here is 0, and when x is equal to a half. X is equal to a half. Okay, so those are the singular points there. Okay, two examples. One more of this straightforward type, and then we will take a look at one where it doesn't have a singular point. Okay, next differential equation. Let's see here. Let's take a look at this. Minus 2y equals 0. Okay, where are the singular points here? Okay, we're a little bit careful because we see the x minus 2 in both places here, but the x minus 2 is not here. Okay, and similarly we see an x here and here, but not here. So we can't sort of divide out these problems. So in this case, the singular points are still at the 2 zeros of this function right here. Singular points. X equals 2 and x equals 0. Now let's just contrast this with the final example here. If I had an equation that looked like this: x minus 1 y double prime plus x minus 1 squared y prime plus x minus 1 cubed y equals 0, there are no singular points, because despite the fact that this is 0 at 1, I can divide that through and rewrite this equation without that problem. So let me just make a note. There's no singular points. We will actually get a little bit more rigorous of a definition coming using a limit, but for now, let us sort of wave our hands around and notice that we could write this like this: x minus 1 y prime x minus 1 squared y equals 0, and then we would have a function here that's 1, and we would not be having any problems with these things here, and we're fine. Okay, so that's the reason. So there's no singular points on this last one, and we're going to be more rigorous about that coming shortly. Okay, this right here, definition of the Euler equation. This differential equation here is important, and it is called the Euler equation. It's sometimes also called the equidimensional equation. Okay, it's linear, it's homogeneous, it's ordinary, and it has variable coefficients. Previously, we've almost always seen, before we started this series, solutions methods, we've always seen constant coefficients. Okay, there are two parameters. There's these alpha and beta. Those are simply numbers. Okay, they're real constants. Some number. They do not change. So you could have many different Euler equations by changing alpha and beta, but once you've chosen them, it's fixed for that differential equation. They're a parameter, not a variable. Okay, our idea of how to deal with this is going to be to transform it into something we've seen before. So my first step to show you why we're going to solve these things in a slightly different method than we've done before. I'm going to transform this into something that we have seen before, and then we'll be able to see how the solution to this equation relates to solving equations that we've seen before. So often a good problem-solving tactic, transform into something you have seen before. Okay, I'm going to write this differential equation out using the Leibniz notation, not just like this, because I'm going to start to use the chain rule, and I think this might make it a little bit more clear what's going on. I'll write this way here. There it is. Now, it's a differential equation. X is the independent variable. Y is the dependent variable. The solution that we would be looking for, y, is a function of x. Okay. What I'm now going to do is make a substitution. I'm going to say let x be equal to e to the t. So I'm going to make a substitution. The substitution is going to transform this differential equation into a constant coefficient differential equation. Okay, that means that once I make the substitution, my y, which is a function of x, will be a function of e to the t, because I'm making the substitution x equals e to the t. Okay, if x equals e to the t, then it is the case that t is equal to ln x. That's simply by taking the log on both sides on the substitution. Okay, so now I need to, I'm going to make this substitution, so I can now easily substitute in for x squared and for x, because I know what x is, and I know what I could just square e to the t, get e to the 2t, and then I can substitute. And what I have to do now is be able to substitute in for these things here. So I know that x is e to the t, and now I need to figure out what is dy by dx. And in order to do that, I employ the chain rule, and that's going to be dy by dt times dt by dx. And that is going to be dy by dt. And then what is dt by dx? Well, there'd, I guess, be a couple of ways I could do that, but I have it sitting right here. So that would be dt by dx. I take the derivative with respect to x here. I get 1 over x, but I know what x is. X is e to the t. So this is 1 over e to the t, and I could write that as e to the minus t. So down here, using the chain rule, I've got dy by dx is, I'm here, dy by dx is dy by dt times dt by dx, and that is dy by dt times dt by dx, which I've just established is e to the minus t. So now I can substitute for dy by dx in my differential equation. I can replace it with this here. I'll have to do exactly the same thing for the second derivative. I mean, I've got both derivatives, the first and the second derivative sitting here. So I'll also need to substitute the second derivative, which is now currently in the differential equation a function of x. I want to substitute it, make it a function of t. So I'm going to calculate what is d2y by dx squared. That is the derivative with respect to x of dy by dx. And using the chain rule, just like I did right here, I took the derivative with respect to x. I said that's the derivative with respect to t times dt by dx. So this is the derivative with respect to t of dy by dx multiplied by dt by dx. That is the chain rule. That is the derivative with respect to t, and I know what dy by dx is. It is dy by dt times e to the minus t. And then I'm going to multiply that by dt by dx, having already computed that. Dt by dx is here, e to the minus t. All right, so this here, this dy by dx, this dy by dx here, this is dy by dx, and that went in here. So let's just keep going. Let's see. So now I'm taking d by dt. I'm going to make this calculation here. I've got a product there, so I'm going to employ the product rule, and I'm going to get the second derivative of y with respect to t both times e to the minus t minus e to the minus t times dy by dt, and then that is all multiplied by e to the minus t. Okay, so I have now going to factor out this e to the minus t, multiply it by that e to the minus t. I'm going to actually write it like this too. That would be e to the minus 2t times d2y by dt squared minus dy by dt. Now here's something that's sort of quite clever. That's going to make this whole thing easier once we make the substitution. Is I can look at this e to the minus 2t here, and then that is 1 over x squared. It looks like I'm sort of going backwards in some way, but I am not, because what's going to happen when I make the substitution up here, I see this x squared here, and then it's going to cancel with that x squared there. That's the idea, because I'm here with the second derivative. This is, don't forget, this is, whoops, let's try that again. Okay, hang on, I got something there I don't want. Let me get rid of that. Delete. Okay. Let us remember that this thing here, okay, let me get that colors back. This thing here is d2y by dx squared. Okay, so I got that 1 over x squared, and then that is going to be here multiplied by this thing here, d2y by dt squared minus dy by dt. Okay, we're actually making headway. We now know, we have our substitution set up that we want to do. We know what the first derivative is, and we know what the second derivative is. So now I can simply substitute in to the differential equation. So I'm going to write the differential equation in terms of x just right here so I could see exactly how the substitution is working. There's alpha x y prime plus beta y equals 0. Okay, so I'm now making the substitution. Here goes x squared, and then I'm going to multiply that by y prime. Y double prime. And there's y double prime right there. 1 over x squared times the second derivative of y with respect to t squared minus dy by dt. And then I have plus alpha x, and I'm going to substitute in for y prime here. So here's y prime right here. That is dy by dt times e to the minus t. What is e to the minus t? E to the minus t is 1 over x. And then I have plus by equals 0. Okay. A little bit of simplifying. Things are canceling out nicely. That is canceling out, and that is canceling out. And I rearrange a little bit, and I get this here. d2y by dt squared plus alpha minus 1 dy by dt plus by equals 0. Et voila! We have now a second order differential equation that's constant coefficient. And we know already how to solve these. That is the good news. Okay, so this thing here is constant. This thing here is constant. So we now have a constant coefficient differential equation. What do? It's homogeneous with constant coefficients. We assume a solution e to the RT. We've been doing this for a long time. So now let's think about this. What is, in this case, what is t? We didn't start with this constant coefficient thing. We have made a substitution. And what is t here? Well, according to our substitution, we have that t is log x. So let me plug that in. So what we're doing is assuming a solution of e to the r log x, and then that is x to the r. So this whole procedure here was to demonstrate to you that when I go to solve the Euler equation, I am going to assume a solution of x to the r, not e to the t like we have been doing. And the reason behind it is exactly this, because in the case where I have looking at my differential equation, I have an x squared here. This particular case, that's an Euler equation. I have an x squared there, and then I have an x following on the y prime term. I can show you via this substitution that substituting e to the t into this equation is the same as substituting x to the r into this equation. So it's an important thing to see that we can. This is a valid way of solving the Euler equation. Okay, with that justification, we are going to now solve the Euler equation, and we're going to start out here with x greater than 0. That's just to make our lives easier when we started talking about x to the r, and then we'll fix the problem later in terms of what to do when x is less than 0. Okay, so we have the Euler equation. Here it is, x squared y double prime plus alpha x y prime plus beta y is 0. And you want to be able to recognize this equation when you see it. It should, when you see this one, you should say, okay, this is an important a differential equation for a variety of reasons, and I recognize that this is the Euler equation. Okay, step one, assume a solution. Assume a solution y equals x to the r. Okay, this is not e to the x like we normally would be doing. This is x to the r. Okay, so then we'll do the same thing that we always do when we assume the solutions. We can calculate the derivatives, plug it back in here, and see if we can identify what that value of r must be. So I'll calculate the derivatives. Y prime is rx to the r minus 1, and y double prime is r minus 1 x to the r minus 2. So we're going to plug that into the differential equation. Okay, so that's going to be x squared, then y double prime, r minus 1 x to the r minus 2, plus alpha x. Let's get that nice so we can tell the difference between the alpha and the x. Alpha x times y prime. What is y prime? That is r x to the r minus 1. And then beta times y. What is y? Y is x to the r, and that's equal to 0. And you're going to see right away why this works so nicely, because what is happening here is that I have x times x to the r minus 1 giving me x to the r, and I have x squared times x to the r minus 2 also giving me x to the r. That allows me to factor out that x to the r. Okay, so let me do that. Factor that out. X to the r times r minus 1 plus alpha r plus beta equals to 0. Same logic that we used before. X to the r is not equal to 0 for x greater than 0. So therefore, this thing here, this polynomial in r, must be 0. So we have here r squared, that polynomial is this, r squared alpha minus 1 r plus beta equals 0. That's the polynomial. And we can use the quadratic equation to see what the roots of it are. That's going to be r is equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. Okay. So that we can compute this, and let me just write that in this format here so I can refer to the roots. That looks like this: r1 r2 equals 0, where r1 and r2 are being computed from this equation right here. So I compute this, I get 2 roots. I'm going to label the first one r1. I'm going to label the second one r2. And just like before, we're going to have 3 cases. We're going to have case 1. R1 and R2 are real and distinct. Then in that case, we will have that y of x. The solution to the Euler equation will look like this: C1 x to the R1 plus C2 x to the R2. That's, again, x greater than 0. Okay, next, case 2, when we have R1 equals to R2 and they're real, so we have a single root with multiplicity 2, we are going to have, then we have one solution right away. That's going to look like this: x to the r. Well, I can call it R1, but R1 and R2 are the same. We have one solution. And then what you can do is use reduction of order. You use reduction of order to find a second solution. Okay, I mean, do this as an exercise. This has nothing in sense to do with the series solutions. From before we've had the situation where we're given one solution to the differential equation, we could find a second one. So use the reduction order to do that. Do it as an exercise, sort of for a review. Oops, review. Okay, when you do that, you will get that second solution, and it will be this. It'll be x to the r1 multiplied by the log of x. Okay, I want you to be seeing the parallels. Before, when we were doing constant coefficient, that this was the constant. We're not in constant coefficient model here, but before, when we were doing these second order equations, constant coefficient, we had e to the r1t, and then we had t e to the r1t. Okay, so there's definite parallels here. So now when we have both the roots being real, we can find directly the first solution, x to the r, and then we can find the second solution via reduction of order, and it's x to the r times log x. So there's strong parallels here. That gives us our general solution, the linear combination of the two functions there. That's going to be c1 x to the r1 plus c2 x to the r1 log x. Okay. And then we have the third case, not surprisingly, the complex roots. Okay, so we're going to have one conjugate pair for the complex roots, and that is going to be r1, and I'll use the same naming convention we did before. That's going to be lambda plus I mu, and r2 is going to be lambda minus I mu. And mu will be not equal to 0, because if mu was equal to 0, we would be in case 2. So we've already handled that, so we don't need to handle that here. Mu is not 0. In this case, we'll get that x to the r is, well, that's e to the r log x. And so that is e to the alpha plus I mu times log of x. So that is, I guess I'm using here r1. There's r1 when I have the lambda plus I mu. r2 is when I have lambda minus I mu. Okay, and I can use my knowledge of complex numbers to separate this in this way. Cos of mu log x plus I sine of mu log x. I've got too many brackets there. There. Okay, and then I will claim without too much justification. Here's what I'm suggesting. You do a similar thing like this with the one with the minus sign. So that's r. You go here, r2 log x. You do the same thing, and you fill that in. And then what do you think about? We have always avoided trying to give our solutions as complex functions. What we have done always is said, if we have a complex valued solution, then both the real and imaginary parts are solutions, and we have combined. So we've got here a solution then that looks like this. Y of x is c1 x to the lambda cosine mu log x plus c2 x to the lambda sine mu log x. Okay, just in case you want to refresh your memory on how to get the general solution such that it has no complex it's not a complex valued function. Refer back, we have done this a few times before already, refer back to theorem 3.2.6. refresh yourself on how to do that. Okay, so the point is, now we're in a, well, we have three possible solutions to the Euler equation depending on the values of the roots of the characteristic equation, and here they are. So there's the three cases, and we have fully solved the Euler equation. Let's just take a look at what the solutions look like. There is a typical series of solutions for when x is greater than 0. This first graph here that we're looking at is, well, they're all going to be x greater than 0, and this is the case of 2 real roots. Okay, so that's the first one that we solved. This comes from Wikipedia, so you can have a look in there for more information, but I got these graphs from Wikipedia. Okay, they did a nice job of illustrating this. Okay, so we have different values of r. So let me just roll back here. We've got here we are looking at this this double roots are real and distinct. Maybe I'll just write the solution function right here. Y equals c1x to the r1 plus c2x to the r2. Okay, so we have solutions here where here the values of r are being specified to give you a sense of what they look like. Okay, but they are real and distinct. Okay, then what do the solutions look like when we have a double root? So this is r1 equals, so this is the situation, r1 equals r2, and that's then some number r. And we have a solution that looks like this. We have y of x is c1 x to the r1 plus c2 log x to the r2. R2 is kind of silly, actually. It's still r1. They're the same. Let me just, in fact, replace it with r. r1 is equal to r2. I'm going to call it r. Okay, so then we can draw the solution curves for that. It's a double root situation, and for varying values there of r, depending on what that actual number is. So that's the double root situation. And then we get the oscillating situation when we have the complex roots. So this is the situation where we have a complex conjugate roots, and our solution curve is looking like this. Y of x is equal to c1 x to the lambda cosine mu log x plus c2 x to the lambda sine mu log x. Okay, so then they're giving you here a drawing. Here is the blue curve. There is sine of 4 log x, so that would be mu. Here is our mu. Mu is equal to 4, and then here is our lambda. There it is. Lambda is equal to 0.2, and then there's the other. The orange one is the other curve. So there's two lines on this graph, the yellow and the blue, and they are both for the case where lambda is equal to 0.2 and mu is equal to 4, and then one is the first, the blue one is the sine, so that is, this one is blue, and then this one here is the yellow. Okay, so clearly, I mean, lambda and mu could be different numbers, and the curves would be different, but this is what the shape of them looks like. So we have now sort of almost complete understanding of the what the solution to the second order Euler, or in this case Wikipedia labeling it the Euler-Cauchy equation. Okay, that we had handled this situation x greater than 0. What happens when x is less than 0? Okay, so we have, why do we separate in the, think about this later in the first place? Because when x is less than 0, okay, so let's talk about this. When x is less than 0, we have the problem of understanding what x to the 1/2 means. Okay, so we're going to deal with this the same way. We're going to substitute it away in some sense. Okay, so we'll deal with this via substitution. Deal with this via substitution. And so we have a differential equation, x squared y double prime plus alpha xy plus beta y equals 0. And we're now x is less than 0. So what we're going to do is say let x be minus t. That means that t will be greater than 0. So I'm going to transform this thing back to a differential equation where the independent variable is positive, because I already handled that situation. So then it's just like the substitution I did earlier. Y is initially it is a function of x, and then once I make the substitution, it'll be a function. Well, it's still a function of x, but x is minus t. Okay, I employ the chain rule. Dy by dx is equal to dy by dt multiplied by dt by dx. And that is, in this case, with a simple substitution, minus dy by dt. And then I take the second derivative, d2y by dx squared, and I take the derivative with respect to x of minus dy by dt, and I employ the chain rule, and I find that this is d2y by dt squared. Okay, so then I make the substitution, and I get what? I get t squared, so x squared. Okay, let's get this. X is minus t, so x squared is t squared. So I substitute, and I get t squared, and then I get y double prime, which is still, well, I'll write it this way so we don't get confused, but it's the second derivative like that. And then I get plus alpha, and then I get what is x? X is minus t, and then what is, let's get that y prime in there. What is y prime? Y prime is minus this y prime here, dy by dx is minus dy by dt, and then I get the rest of it, beta times y. And then if I get rid of those minus signs and I rewrite this in this manner, now thinking of y as a function of t, the independent variable is t and the dependent variable is y. I have now, in fact, the exact same equation, but it is for t greater than 0, and that is for x less than 0. So the entire solution process that I did before now applies to this equation. So the solution I generated, in fact holds earlier, holds for x greater than 0 and for x less than 0. Okay, so then I'm going to write that out. So then I can say, okay, for x not equal to 0, we have a problem when x is equal to 0. There's no doubt about that. So let us just put that off for a second. Get rid of that thing. Delete. For x greater than 0 and for x less than 0, we have a solution. So that means we have a solution for x not equal to 0. And that solution is R1 not equal to R2, R1, R2 real. We have the solution y is equal to C1 absolute value of x to the R1 plus C2 absolute value of x to the R2. Okay, and then we have R1 equal to R2 real. We have that the solution to the Euler equation is C1 plus C2 log absolute value of x to the R1, and we have the R1 R2 complex conjugate situation, complex, we have y is the absolute value of x to the lambda, c1 cosine mu log absolute value of x plus c2 sine mu log absolute value of x. Okay, so we have now a solution to the Euler equation for all x except x equals 0. Okay, as promised, as you've no doubt been waiting for, here we are going to get a much more rigorous definition of what is a singular point. And so we're going to do that by looking at some limits. And so we're going to take the limit as x approaches x naught. So x naught is the value that makes p of x equals 0. So let me just make a note of that. P of x naught is equal to 0. Okay, so we look at this function here, and we observe for which values is the argument, is that thing equal to 0. And then we take the limit as x goes to x naught of q of x over p of x, and the limit as x goes to x naught of x minus x naught squared of r of x over p of x. If both of those limits are finite, then x naught is a regular singular point. Okay, so singular points have two possibilities. They can be regular, or guess what? Irregular. Okay, so first of all, we had this, and we also had, so there's a division of the points that we can talk about the series solutions into. We have ordinary points. Okay, this is our first division, and we had singular points. So that was our first distinction. And now we're seeing that there's a distinction actually in once we've identified that we've got a singular point, then we're going to look and see whether it is regular or irregular. Okay, and this is how we're going to tell, by using these two limits. Okay? It's a little bit of a measure of how serious the singularity is. So the regular singular points are easier to handle. So let us just take a look at a couple of examples. We'll see an example of a regular singular point and an irregular singular point. So let's do the slightly easier one first, and then we should be able to distinguish. So we're going to have here, taking this differential equation here. Here it is. There's a differential equation. I think we had this in our first example to identify the singular points. So on our first slide, we had identified that x equals plus or minus 1 are singular points. Okay, now I'm going to ask, are they regular or irregular singular points? So I've got this function p of x, that's 1 minus x squared. I've got this other function q of x, that's minus 2x. And I've got the function r of x being 4. So I take the limits, and I have to do this for each of the singular points. They both work the same in this case. So I'll do x equals plus 1, but they're both the same. Okay, so what you do is you take then the limit as x goes to 1 of x minus 1 times q of x over p of x. I'm going to write p of x like this. Okay, that is 1 minus x squared. I'm going to take that limit. This clearly cancels, and with a minus sign there, so that becomes then the limit as x goes to 1 of 2x over 1 plus x, and that is 1. That limit, it exists, it's finite. Okay, then I proceed to the next limit. I take the limit as x goes to 1 of x minus 1 squared multiplied by r of x, which is 4, divided by p of x, which is still 1 minus x and 1 plus x. Okay, and you can see what happens is that one of these cancels with, well, that cancels with one of those in the numerator, in this manner here. The limit as x goes to 1 of x minus 1 4. I guess I factored in some sense that thing in there. And then here's 1 minus x and 1 plus x. And that's the limit as x goes to 1 of minus 4, x minus 1 over x plus 1. And that is equal to 0. That limit exists and it is 0. Okay, that is finite. Both limits are finite. So that's what I'm noticing. Both limits. Okay, I'm just going to leave that this time, bumping something on the keyboard. Both limits are finite. Therefore, x equals 1 is a regular singular point. In some sense, it's not too bad. We can deal with this one. Okay, let us take a look at a singular point that's a little bit more difficult to deal with. Here's an example. Next example. Here it is, the x cubed y double prime minus y equals 0. So in this case, we have the functions as we've been labeling them, p of x being x cubed, q of x is 0, and r of x is minus 1. So we take the limit. The limit as x goes to 0, the singular point x naught is 0, and that's going to be x minus 0, x minus x naught, times q of x divided by p of x. And I've got x over x cubed. So let me just, well, I've actually got 0 over 0. I've got x times 0 over, let me try to write what I'm saying here. X going to 0 of x times 0 over x cubed, and x is going to 0. Okay, and the other limit, what does the other limit look like? The other one is the limit as x goes to 0 of x minus 0 squared times minus 1 divided by x cubed, that's p of x, and then that looks like this, minus, or the limit as x goes to 0 of minus x squared over x cubed, and so that is the limit as x goes to 0 of minus 1 over x, and that is infinite, and this one here is 0. But this problem right here is not finite, so x equals 0 is a irregular singular point. So this is why we were spending actually quite a bit of time on this, and why is that? So that is because of this absolutely, I think, remarkable fact, which I am noting here. So all, this is a very strong statement, all equations of the form px y double prime plus qx y prime plus rxy. So all of these second order differential equations that are linear and homogeneous behave like Euler equations near their regular singular points. Okay, so let's make it just a couple of notes here in conclusion. At a singular point, y of x may not have a Taylor series. So that presents a problem for doing to finding a Taylor series. You want to make sure that you're looking for something that exists. So our goal, and we're going to resume with this in the next lecture, is to adapt the series solution method for ordinary points. We've seen that in the previous two lectures, how to use a series solution method for solving differential equations near ordinary points. Now we've got a sense of, first of all, how to solve the Euler equation. We also know how to tell which points are singular, and we know that we can identify two different types of singular points. So now our goal is going to be to adapt the series solution method we already have for ordinary points, so that it also applies in the neighborhood of a singular point. Because that is what is coming in the next two lectures. Thank you very much, and see you in the next lecture.